Hello, everyone. This is my first video ever uploaded to YouTube. It is a presentation required by an undergraduate astrophysics course. Today, I am going to talk about the topic of fast radio burst, which is an evolving mystery still not fully understood by humans. I will start with the background led to its discovery, then introduce the first observed fast radio burst and conclude some characteristics of this anomalous astrophysical phenomena. Thereafter, I will briefly introduce two possible explanations of fast radio burst based on the models of Magnetar, and end this topic by the limitations of the physics models that explain fast radio bursts. So, let's get started. Radio astronomy is a very new area compared to people's optical observation of the sky. It has a history of just 100 years. It was first used to study quasars. Quasars are basically supermassive black holes that have large accretion disks. They are extremely bright and far from the Earth. And the technology of our radio telescope had improved by more accurate demands for this observation. One of the most significant achievements of radio astronomy in the 20th century is the discovery of pulsars. As is shown on this picture, a periodic signal was received at that time, and it was confirmed that they were originated from a rotational neutron stars like lighthouse. Here we introduce a concept called dispersion measure DM. Keep in mind that it does not stand for dark matter under this topic. DM is the integrated density of the free electrons along the path of the light. And DM together with the galactic model provides us a way to estimate the distance of the observed event. Next, fast radio burst was discovered under the background that our radio technology was sensitive enough to capture a very short but strong signal. The first fast radio burst was called Lorimer burst in 2007. It was too bright, 10 orders of magnitude brighter than any observed signal at that time, and its high value of dispersion measure suggested it was located as far as 1 gigaparsec. Thereafter, such an astonishing, intense flash of radio signal within milliseconds is defined as fast radio burst. In astrophysics, brightness is directly linked to energy output. Take the first confirmed fast radio burst as an example. It released 10 to the power of 33 joule in just few milliseconds. That is the total amount of energy that our sun can produce for 100 days. Also, the size of region such thing happened was rather small. Therefore, they are believed to be catastrophic even in astronomical scale, that can only be produced by some extreme objects such as neutron stars or black holes. Until now, even if much more fast radio bursts have been observed by us, we still have no idea what they are for sure. Besides, they are not so rare and may happen repeatedly at the same location. Among many candidates, Magnetar is believed to be the possible source of fast radio bursts. Magnetar is a special class of neutron stars that is horribly strong in their magnetic field, although neutron stars are already generally strong in their magnetic field. So, neutron stars are even much scarier than black holes that you won't want to approach because their magnetic field will tear you apart long before you reach them. So, what is the evidence that relate fast radio bursts to magnetars? It was the observation that happened on April the 28th, 2020, which was confirmed by radio arrays at different locations on the Earth. We are excited about this event because it supports the postulate that magnetars are the source of fast radio bursts. The source of this fast radio burst coincided with one of the known magnetars within our galaxy. Previously, magnetars were suspected because their radio pulses are too weak to be classified as fast radio bursts. However, this time, even though it was still around 30 times weaker than typical extragalactic fast radio bursts, it was already thousands times stronger than pulses from a pulsar. Above all, this discovery implies young active magnetars can produce fast radio bursts. Knowing what, where, and who produces fast radio bursts, the next question is how. So here I will brief about two models. One is close-in model, and the other is far away. They are proposed in different academic papers. Let's focus on the close-in model first. Close-in means closer to the surface of the neutron star. Fast radio burst is generated by the sudden release of energy by Magnetar's magnetic disturbance, such as earthquake. It will produce a peak of electromagnetic radiation. Then the alpha wave is generated with disturbance, which describes the oscillation of the magnetic field along the field lines. This model assumes the magnetar performs like a magnetic bar, with field lines diverged near the poles and closed near the equator. Such geometry will cause alpha wave reach distance farther near the poles, several times of the radius of the neutron star. Besides, the charge density near the neutron star goes lower farther from the surface, and this will result in charge starvation because the propagation of the alpha wave requires charge density. Then, the damping of the alpha wave will form an electric field along the magnetic field line. When a clump of charges is driven by the electric field along the magnetic field line, a coherent curvature emission will occur. On this page, I supplement some explanations about the close-in model. The amplitude of the alpha wave decreases with the radial distance to the power of -3/2. At the starvation distance r, with lower index starv, the charge density is critical required by alpha wave. In addition, the fast radio burst is accompanied by X-ray bursts. We may investigate the energy ratio based on this model. The energy ratio is related to the inverse ratio of the radius to the power of 3. From the observation, only 1 out of 1,000 X-ray bursts is accompanied by fast radio burst, which implies the starv radius is around 20 times the radius of the neutron star. Based on the starv radius under this condition, the duration of the burst is estimated to be 1 millisecond. It is reasonable to the actual timescale. On the other hand, there is another faraway model to explain the fast radio burst from a magnetar. In fact, this model even generalizes the central engine from magnetar to any possible compact objects that able to eject relativistic flares. In this model, a blast of ultra-relativistic plasma is blown from the central engine, then collides with the ionized material from previous ejections. It forms a shock, and the forward shock wave will generate coherent radio emission by mechanism called synchrotron-Maser mechanism. The polarization of the fast radio emission is determined by the magnetic field in toroidal direction, then reduced by Compton scattering. The X-ray emission can also be generated under this model. Well, here I put another diagram showing intuitively the mechanism of synchrotron-Maser. We can see the radio emission can be generated when charged particles gyrating around the field line coherently. Okay, that is all about my very rough introduction on the models of mechanisms of fast radio burst. Essentially, they are just hindsight that attempt to account for the origin of the fast radio burst from a magnetar. And of course, they have their drawbacks and limitations that do not fit the observations well. For example, in close-in model, we assumed the geometric shape of the field lines like a magnetic bar. The real picture of the magnetic field around a neutron star can be very complicated, while the charge starvation model also sensitively depends on the charge profile near the neutron star, which can also be complex. And the ratio between radio wave and X-ray is not fixed. The mechanism must adapt for these changes. What's more, the formation of the synchronized curvature radiation remains unclear. For the faraway model, it has the problem that it predicts more X-ray than most of the observation, and the bandwidth of the radio emission can be large due to the complex shock conditions. Also, such emission does not fit well with the timescale up to milliseconds. Finally, the generation of the ultra-relativistic plasma is hard to realize. There are many flaws for both models. Therefore, the mechanism and the origin of fast radio burst still remain mysterious to us. However, fast radio burst is expected to be a good probe, like quasars, for us to understand the models and phenomena of the universe better. Research and investigation into this bright radio firework are expected to evolve and remain active for the coming decades. Okay, that is all for my presentation. Thanks for your watching.